where we had actually a number of years overlap. In that time, he unfortunately did not really appreciate lattice QCD, but finally he discovered it and did a lot of very good work in lattice QCD for nuclear physics. And then he got a faculty member at Carnegie Mellon and finally a position at the University of Washington. And then in 2013, he became a member of this Institute for Nuclear Theory. Martin did really very pioneering work in effective theories for nuclear physics. And then he did a lot of work, as I said already, in lattice QCD. And recently, he got interested in quantum computing. And he has already publication for this topic. And I'm really looking forward to see what we might be doing with quantum computing for nuclear and high energy physics. Thanks, Martin, for coming here.
Thank you very much, Carl. It's a real pleasure to be here. Is my microphone on? So how I got into quantum information, quantum computing, and it's only been during the last few years, last 3, is because I was involved in the exascale projects, and in particular determining with others in the nuclear physics community the classical high-performance computing resources required to address the grand challenge problems in nuclear physics. And so this was a 1.5 year long process, and at the end of that process, there was still important observables and processes that we wanted to calculate in nuclear physics that were beyond exascale, both in memory requirements and also in cycles. And so if you looked at what the defining characteristics of those problems were, they were all finite density problems and also problems involving dynamics. And so that is what pointed others and myself into thinking about alternate methods beyond exascale computing, and quantum computing was one of the things we looked at. And so one of the objectives of nuclear physics research is to start from the theory of quarks and gluons, as you're familiar with, and then systematically compute the problems of interest through all the length scales of relevance in nuclear physics. And so hopefully that means going from the very smallest at the Fermi and below length scales through nuclei, through nuclear dynamics, and all the way through to astrophysical objects and everything in between. So that's the ultimate objective. We know what the laws of nature are relevant for nuclear physics. That's the standard model of particle physics, which is the strong force, the electromagnetic force, and the weak interactions, and those should be sufficient to define all of the observables and allow us to compute the observables we want with arbitrary precision, as long as we have the calculational technology. So I want to go through some of the challenges here. So nuclear physics in the United States, I think, is defined a little bit differently to Europe, so it's going to get a mix of HEP and NP in here. So one of the important problems, of course, is we want to be able to start from the earliest moments of the universe and be able to calculate using the standard model all the evolution of the earliest moments of the universe all the way through to present day. This is, and really what I mean by that is to really start calculate through the phase transitions, the generation of baryon number, and all the way through to the production of nuclei. So this involves a couple of phase transitions at least, and has non-trivial field theory aspects to it, and that's an understatement. And so on this diagram, this is the phase diagram for QCD, where we have baryon density and temperature. And so really we're going to be starting from the situation where we have a quark-gluon plasma all the way through the near-perfect liquid phase that was discovered quite a number of years ago now at heavy ion colliders, and then all the way through to atomic nuclei. And so if you look at where we are experimentally today, then theoretically we know that as we increase temperature at zero baryon density, there's a smooth crossover. And there's a couple of experimental facilities that are probing this phase diagram. One in the US is the relativistic heavy ion collider at Brookhaven, and then of course we have the major facility at the LHC. These probe significantly different areas, if you like, of this phase diagram. And there's currently a program underway during the next few years to look for a potential critical point in the QCD phase diagram. So if you look at some of the static quantities that we're interested in QCD and in the standard model, things that we want to look at that are accessible to us experimentally, one is the structure of the nucleon and the structure of low-lying baryons. There's been considerable study of this during many decades, and we're at the point where we have a relatively good understanding now of, for instance, what is the spin decomposition of the nucleon and what is the mass decomposition of the nucleon. This is being delivered to us both experimentally and also through lattice QCD calculations. And then, for instance, there's states of matter that can't be understood in terms of just quark-antiquark pairs, for instance, in terms of mesons, and one really explicitly needs to have dynamical gluons, and this is something that we're also addressing theoretically with large-scale high-performance computing computations. We have the structure, we have nuclei themselves, so nuclei are kind of interesting objects. You think about a nucleon, which is essentially a maximally entangled system of massless particles and near massless particles of indefinite particle number. And then you think about what a nucleus is. A nucleus looks like, to a good approximation, a collection of neutrons and protons. The interactions between neutrons and protons are dominated by the two-body interactions. The three-body interactions are significantly less important, and there's no statistically significant evidence for four-body interactions. And so you ask, why is the nucleon this non-trivial entangled system, whereas a nucleus really looks like it's collections of neutrons and protons, and is not, and it doesn't collapse just into a system of gluons and quarks. On the fundamental symmetry side of things, there's programs underway internationally to look for double beta decay of nuclei. This is, if one was able to observe a neutrino double beta decay of a nucleus, then that would be unambiguous evidence for the violation of lepton number, which would be indirectly, in most instances, an indication of baryon number violation. One's also looking for violations of other fundamental symmetries, and of course an important one is time reversal violation. Okay, let's give this a go.
No, you have to do this again.
Let's try this.
And it's on.
Okay, thank you. Yeah, that sounds better.
Yeah, that's true. That's for singing.
Okay. And so here one's looking for an electric dipole moment of a fundamental particle like an electron or a neutron. Time reversal violation hasn't been observed before, and so this would also be discovery of the violation of a fundamental symmetry, even though we expect it to exist through basic field theory relations and so forth. On the side of nuclei, there's, of course, hundreds of years worth of investigation into nuclear physics. A side note, as I grew up in New Zealand and I went to Rutherford High School, and I had no idea of the significance of that name until I was at university or quite late on. So I'm not quite sure whose fault that was. I'm sure it was mine. So if you look at the progress we've made in performing computations of basic properties of nuclei over the last 30 years, this is a figure showing the size of the nucleus versus year, and you see that there's been steady progress, and then it's really picked up recently. And the recent pickup was for a couple of reasons. Firstly was of course, the capabilities of leadership class computers, and also the ability of our community to use such computers. But it was also the introduction of new techniques into the field, and perhaps this is the more important point. Around about here, in this period, technology from the particle physics community, particularly the renormalization group and effective field theory, moved into nuclear physics. And so a lot of this progress was the fact that now the renormalization group is used to soften the interactions between nucleons. And so instead of having a very hard core in the low energy spaces, one is able to use the renormalization group flowed interaction, it's softened interaction, and so one can work with much larger model spaces. And so it's a combination of both high-performance computing, but then technologies from other fields that have been brought in over a 20-year period or so that's actually allowed this progress. And so that's an important point because we're at a similar stage now when it comes to quantum information, quantum computing, and a lot of the technology from that community that's now just barely starting to move it into both NP and HEP. So this is again a very US-centric picture. This is the funding agencies have the communities organized. So this is one collaborative organization that's been put together to be funded to actually perform these projects. It involves collaborations between computer scientists, applied mathematicians, and domain scientists, nuclear physicists, and others. And it's this collaboration of people with a broad range of expertise has actually been one of the things that's actually allowed this program to move forward. And I show this picture here. Essentially, this is completely off topic, but I like it. And so what is shown here is a density profile of neutrons and protons in the outer regions of a neutron star. And you see it has a parking garage structure. And so what that means is you have some parking level, and then there's a spiral ramp that takes you up to the next level, and there's a spiral ramp that takes you up to the next level, and so forth. And that's the sort of structure you find in nuclear matter as you move towards the outer regions of the star. And this is a similar parking garage structure, but this is found in terms of molecules in the interior of a cell. So this is a biological structure that's found in cells, and this is a nuclear physics structure found inside on the outer edges of one of these. So basically it's just a statement that the effective Hamiltonian in this low energy space has many similarities. And then in nuclear astrophysics, again, there's been major progress, and the sensing and the observatories are now quite remarkable and span both different spectra and a larger range of spectra. And so you see these space-based satellites, both in the X-ray and over a large range. And in fact, of course, we're all fully aware that gravitational waves have been detected. And from a nuclear physics point of view, so this is the signal that was observed. If you Fourier transform the signal, then the high frequency components of this of binary neutron star coalescence, the high frequency part corresponding to the ringing of what's left of the combined object, the frequency of that ringing is dictated by nuclear physics, how stiff is nuclear matter. And in fact, at the moment, we don't have the theoretical capabilities to predict that with enough precision. So there's some uncertainty in the high frequency components of this curve, the predictions of this curve, due to the limited understanding of high density nuclear matter. So onto the computing side. So high-performance computing has been central in the developments in nuclear physics. And this, of course, this is classical computing. So if you look at the experimental program, then the design and optimization, this is about a 1.2 billion operation in the United States, and the facilities support about 4,000 users. The high-performance computing is critical in the design and the operation of these experimental facilities as they are worldwide. It's also now becoming increasingly important in the acquisition and handling of experimental data. It's always been important, but it seems to be the amount of data now that's being collected is growing significantly. And it's also critical in large-scale simulations and calculations of the emergent complex phenomena that we have in these quantum many-body systems. It ranges from subatomic all the way through to cosmological. So, changing gears a little bit, so at the subatomic level, the theory that we've been working hard to solve is quantum chromodynamics, and there's a number of experts in the room that have made pioneering contributions to this field. And so the basic setup then is that you want to solve a continuum theory in infinite volume, which is quantum chromodynamics in our universe. With any computational device, you have finite resources, and so one has to truncate. So one works, instead of with a space-time continuum, one works with a discretized space-time lattice. Instead of infinite volume, one has to work with a finite volume. And then one takes the quantum field theories that you want to solve, in this case QCD, and discretize them and puts them onto the space-time grid. Now, what we've been doing with classical computing is working with Euclidean spacetimes where, where correlation functions fall off exponentially in the time direction. So this is a very well-defined method, and as long as the lattice spacing is small compared to the scale of the physics you're interested in, and the volumes are large compared to the scale of the physics you're interested in, then one can perform a series of computations over a range of discretizations and a range of volumes, and then use well-defined theoretical frameworks to extrapolate to the continuum and to infinite volume. So this is taking the continuum limit, taking the infinite volume limit. And the reason I'm stressing this is, I'll come back to this later in the context of quantum computers. Now, one views this as an effective field theory. So this is a picture of the dispersion relation. So in the horizontal axis is particle momentum, and the vertical axis is the energy of that particle. And so as long as the momentum is small compared to the discretization scale, then one reproduces well the dispersion relation. On the other hand, when the momentum becomes large compared to the inverse lattice spacing, or comparable to the inverse lattice spacing, when you can actually probe the fact that space-time is not a continuum but discretized, then you start seeing deviations from the dispersion relation that you want. And so the dispersion relation on any space-time lattice you'll see is not the red cone, which is what you want, but is in fact this orange surface where it behaves exactly like it tracks the cone until it gets out to order 1/a, then it flattens off and becomes some mess. So as long as you're doing calculations that only probe this part of the dispersion relation, then you'll recover the answers that you want. But if you start probing further into the ultraviolet, you'll start seeing the limitations of your low energy effective theory. So lattice QCD is one of the big drivers for high-performance computing. It takes a significant fraction, significant of order 10% or less of the world's computer resources. And so understanding the actual resources required to solve particular problems has been important and will continue to be so. And so as an example, a few years ago now, about 4 years ago, as I said, we estimated the requirements needed to solve particular problems. For instance, the structure of these exotic states, multi-nucleon forces, double beta decay, and so on. And so you see, you're talking about running an exascale machine for 1 to 10 years, for instance, in this region of the plot, and this is sort of cloud-type computing, but again, you have of order exascale scale cloud-type compute resources required. And then also the amount of hot data versus cold data is significant. It's 1 to 100 petabytes or so. And so these are all large numbers to address these particular scientific challenges. And as I mentioned, the challenges that are really often the multi-exascale and beyond are the finite density systems. So, for instance, as you want to perform computations of nuclei, in terms of quarks and gluons, if you want to look at the behavior of mapping out supernova explosions and so forth, it's the finite density aspects of that, or that's one of the drivers for these large resources. And then explicit time evolution. Explicit time evolution, we didn't actually really consider that seriously because it was off the scale, because it scales so poorly for classical computation. So the sign problem, we heard about this morning in some really nice presentations. With any finite density system, with Monte Carlo calculations, one is sampling. One is sampling the partition function and performing and taking expectation values. And so as an example here, if you want the expectation value of the operator O, you perform an integral over the gauge fields, you evaluate your operator O in a particular gauge field, and then you weight it by some probability distribution, and at zero chemical potential, this object in particular is a real number, so that makes sense. On the other hand, as you increase the chemical potential by going to increased density, then this acquires a complex phase. And so for a small phase, one is able to brute force sample your way through that and determine the average value. On the other hand, as the phase becomes larger and starts wrapping around the circle, then you just can't, the computation won't converge. And so that's the problem that we have, and Christoph Sitchi's talk this morning was I don't need to really repeat that. It was such a nice presentation of the fact that for the systems of interest in this region here, the classical computational costs are very large as a result of this type of sampling issue, whereas down here one's able to perform in this region here quite brute force calculations, and they actually seem to converge. In the area of fragmentation, so this is a common problem for high energy physics and for nuclear physics. One is not in a position at the moment to start from a high energy collision of, for instance, a proton and evolve that system all the way through to the particles entering your detectors. The reason for that is you have to, in Minkowski space in real time, track, for instance, the evolution of a quark-antiquark pair produced in the decay of a Z0 through the entire process of radiating gluons, radiating quarks, and then ultimately turning into the low-lying hadrons that are stable and the objects that actually into the detector. So this the complication here is one needs to keep track of the phase information with all of the quantum numbers throughout this entire evolution. And at the end of the day, all of the states that enter your detector are paired up in such a way to be color singlet objects. So there's a very sophisticated phenomenology that works remarkably well. However, one is not able to start directly from these high energy processes and go all the way through to the hadrons from first principles. So these are the motivations that have led us to think about quantum computing and quantum information. And I'm coming at this problem from more of, I don't want to say an engineering background, but I think that's really what it is. I'm coming at it from seeing these are the problems, what do we have today, how can we move forward to trying to go from this initial place where we are to solving these problems. So which means that there's a lot of learning on the way, and during the last few years I've been learning. And so, for instance, consider a quantum device or both a classical and a quantum computer made of 3 bits. So I've got a picture here. These are qubits. And so, for instance, this could be an electron or any other spin half system, and one is able to perform quantum unitary operations on this system. And so if you have a classical computer and you have 3 of these bits, then your classical computer can be in any one of these 8 states. So your computer could be in 0, 0, 0, or 1, 0, 0, or 1, 1, 0, any of those 8. At any one time, when you look at the state of the computer, it's in one of those states. And so then you can perform an operation on it. For instance, you can start in the 1, 0, 0 state and then change this bit from a 0 to a 1, and then you end up in this state here. So a quantum device has the same number of states. It has 8 states corresponding to the states of the 3 qubits, the z orientations of the 3 qubits, but the big difference is that you can put this computational device into a linear combination of all of those states at once. So you can put this quantum device into, for instance, this state, which is alpha 1, 0, 0, plus blah, 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 all the way to the end. And so then when you perform an operation on this state, so you take a unitary operator and you perform a unitary operation on the state psi, you're actually operating on all of these basis states at the same time. So instead of operating on the classical states, acting on this one, and then acting on this one, and then acting on this one, you can actually, on a quantum device, you act on all of these states at the same time with the same operation. And so when it comes to the actual operations, one has to think about things in terms of quantum circuits, and I don't want to dwell on this too much because there's a lot of technical things here, and it's... However, so for instance, if you have 2 qubits, for instance, and these lines denote the qubits and the actions on the qubit. So for instance, you can act, this is, if you want to perform a general U4 operation on this 4-dimensional quantum state spanned by that's created by these 2 qubits, then for instance, one can perform a controlled issue 2 operation acting then with a Hadamard gate, acting with a controlled issue 2, with a Hadamard, a controlled issue 2, and then an anti-controlled issue 2. And that gives you a complete spanning of the U4 space. And so this actually provides a recursive algorithm because you can generate then any issue 8 transformations by having this type of sequence on a 3rd qubit with now issue 4 rotations acting on the combined system. So there's a number of recursive algorithms that one can perform acting on these quantum systems to completely span out this simple 2 qubit computer. So what is the potential of quantum computing? And this is a slide that Dave Wecker gave, that Microsoft gave at INT about a year or so ago, and I can't really improve upon this slide. So, and so what you see here is a plot of the computational time versus the number of atoms. And so this is to define, for instance, the ground state energy of a complex molecule with this number of atoms. With a certain level of precision. And so you see on a classical computing device, one has exponential dependence. One of the characteristics of a many-body problem is it depends exponentially on the number of bodies. And so you see this classic, the time to solution, for instance, depends exponentially on the number of atoms, whereas on a quantum device, it scales polynomially. And of course, there's an offset here, because we can do small atoms. We can do small atoms with classical devices, and we're still not able to do them on a quantum device yet. Well, that's not entirely true, but however, there's going to be an offset, and so however, once you get past this point here, then you can actually do much larger systems with quantum devices, and you'll never be able to do them with a classical device with the desired level of precision. And so, for instance, 100 qubit devices can address problems that are beyond classical computing. And so and so with a 50 qubit system, you look at the dimensionality of the Hilbert space, then it roughly corresponds to about 20 petabytes of memory on a classical device, which is currently the size of leadership class compute facilities. And then if you have 300 qubits, then you have more states, roughly 10 to the 90, then you have the number of atoms in the universe, which is about 10 to the 86. So with 300 qubits, the dimensionality of the Hilbert space, you couldn't even build a classical computer from all of the atoms in the universe that would actually be able to span that space. So that's quite a startling number. So if one's looking, for instance, here's an explicit example, again a slide from Dave Wecker, looking at the computations to find the ground state of ferredoxin, which is a simple molecule. Then a classical algorithm, it's intractable. It can't be done. So then the quantum algorithms that were in place in 2012 would allow you to perform this computation. It could be done, but it would take 24 billion years. So from my point of view, that's also intractable. However, it's a number that you can write down. Then after about 3 years of algorithm development and trying to understand how to improve the quantum circuits and so forth, then it turns out you can actually perform this computation with less than 200 perfect qubits in about an hour. So this is remarkable. It shows firstly you can do something on a quantum computer, or you expect to do something on a quantum computer you just can't do on a classical computer. And it also really demonstrates the value of having teams of people think about trying to solve a particular science problem and develop algorithms and conceptual developments to actually take you from something that's effectively intractable to something that can be done readily. So at the time of the exascale, evaluations were underway and the resource estimates were being made, some technology companies in the United States, and again I'm giving you a US-centric viewpoint, but the technology companies in the US were starting to make simple quantum computers available through the cloud. So the first one was IBM, where you could actually send them an email and they would send you a token and you could get on and do and perform quantum computations on small quantum devices starting with 4 and 5 qubits. And so what you're seeing, and what started a while ago, and what you're seeing is technology companies, national laboratories and universities working together to develop hardware. And the technology companies are starting to make simple devices available via the cloud. And as you'll see in a little bit, they're not so simple anymore. They're pretty serious devices. And also the laboratories and companies are making hardware available through collaboration. And so this is primarily, for me at least, I'm in a collaboration through a national laboratory, and so that's how we're getting access to the technology company devices. So motivations for nuclear physics, there's a few of them, roughly summarized, and something I haven't spoken about is sensing and detection. I'll say something about that in a minute. But certainly quantum information, quantum computing has the potential to provide improvements in sensing and detection, to perform controlled large-scale simulations of quantum many-body systems and of the Standard Model. And one has to keep in mind that the quantum computations, they're not expected to replace or be a substitute for classical computing. There's going to be a number of things that classical computers are going to do very, very well during the exascale era, but these should really be viewed as complementary. The quantum device is complementary to classical computing, allowing you to address the problems that classical computing struggles with, particularly these finite density and time evolution problems. And it's also expected to transform how one handles data. And it's important to keep in mind that there's no explicitly demonstrated quantum advantage yet for any scientific application. There's theoretical proofs and theoretical estimates, as I showed you on previous slides, but in fact, when it comes to the hardware getting onto an actual device, there's actually no explicitly demonstrated quantum advantage. And, sorry? Yeah, but, that's right. This is an important word. It's coming. And I should also add that the Rigetti technology company in the US has offered a prize of $1 million for any person or team that can actually show a real quantum advantage. So if you ever needed any motivation, there it is right there. And I'm being sarcastic, of course. Okay, so on the quantum many-body systems, so finite density systems, you know, they're typically attacked with classical computing quantum Monte Carlo. This is probably going to persist through into quantum computing. And the issues that we heard about this morning, the sign problem and sampling, that's a real limitation as one increases the density. And then for the nuclear many-body problems, for instance, one typically uses the Schrödinger equation. And the Hilbert space, as I mentioned before, grows exponentially with the number of bodies. So this is currently one of the limitations in dealing with larger nuclei, is the fact that the time to solution, the dimension of the Hilbert space grows exponentially. So classical computing, you have exponentially large resource requirements and exponentially growing memory requirements. In quantum computing, there's no sign problem, and I put the word naively here, and I'll come back to this. One's able to perform real-time evolution. So fragmentation, for instance, in quantum field theories is now is now a target. The Hilbert space grows exponentially with the number of qubits. So what that means is that every time one adds a qubit, you double the size of the Hilbert space that you get to work with. So as far as the standard model is concerned, one's interested in many aspects of quantum field theories and fundamental symmetries. You're dealing with systems of indefinite particle number, and you're dealing with theories that have gauge symmetries and constraints. So these are non-trivial features that one has to deal with, both on the classical side and on the quantum computing side. And also these theories have non-trivial topology, which is interesting for formal reasons, but also, as we've heard about during this meeting, also for practical reasons. And the real-time integration, the issue really is integrals over phases, the fragmentation, as I mentioned, but also, for instance, other phenomena that are important for astrophysics and nuclear astrophysics, and that is the evolution of neutrinos in dense matter. This is a nonlinear problem involving where you have to keep track of phases, and this is something that quantum computing, that's very difficult for classical computing, but is something that should be much less difficult for a quantum device. And so typically classical computing, you work in Euclidean space, high-lying states, so excitations are difficult to get at. There's signal-to-noise problems one encounters, and there's severe limitations for real-time processes. And with the quantum device, you can do real-time evolution. You can construct your calculations in such a way to directly access S-matrix elements, even ones that are highly inelastic, and there appears to be no sign problem. So the important thing about this meeting, one of the important things about this meeting that I really liked is it's bringing the communities together. So there's a number of communities represented, and it's going to take that sort of cross-fertilization and collaboration to take advantage of these new ideas in quantum information and quantum computers, and to go from a quantum device all the way through to predictions in the domain sciences. So, how long do I have, Carl? 20 minutes. Okay, thanks. So let me just say a few words about sensing. So this is well outside of what I understand at a deep level, but at a fairly superficial level, for instance, one thinks about detection and one thinks about classical detection. And so if one has a target, for instance, and you're looking for a new type of particle, for instance, that interacted with a nucleus, or a fundamental particle with an interaction that depended on sigma z, as an example, then one has a target composed of many target particles, and so these interactions would look like tensor products, and so there'd be potentially 1 over root n type scaling for the precision of the measurement for n targets, with a gap here that's, say, x. However, if you could actually entangle these targets, so this century of detection, if you could actually entangle these qubits so they were not a tensor product but actually entangled, then this gap doubles. This gap is now double this gap, where you flip 0, 0 state to the 1, 1 state. And so, for instance, here you would detect 2 particles with the gap 1. Here you detect both particles at once with the gap 2, and you actually find that the uncertainty scales like 1 over n as opposed to 1 over root n. So there's enormous potential here for improving sensing and detection of weakly interacting fundamental particles or not fundamental particles, and the potential factors here are square root factors of n. So they're not exponential, but they're square root factors, which are substantial. Let me just skip that. So John Preskill coined the term the Niska era, so the noisy intermediate scale quantum era, which is what we're in now and will be in for the next decade, most likely. And so these are quantum devices and with quantum qubits that have little or no error correction. And to do error correction, a lot of the discussion in the meeting so far, there's a number of experts here, more expert than I am. So you see the number of qubits is greater than 10 times the number of qubits to actually get an error-corrected logical qubit. One expects to have a few hundred qubits that can sustain a modest gate depth before these quantum devices decohere. The gates are far from perfect. And it has to be understood that this is not a magic bullet. It's not going to replace classical computing, for instance, for calculating the mass of the proton. It's going to be done with classical computing with high precision long before quantum computers will get to it. And it's important now during the next period for us to understand the scientific applications where quantum could actually provide a quantum advantage. And that process is just now starting. So the structures, and again, this is beyond my expertise. This is a slide taken from an article in Science from a couple of years ago. There's a number of different types of candidate qubits, or demonstrated to be qubits. Firstly, one has superconducting loops. One has trapped ions. There's silicon quantum dots, topological qubits, and diamond vacancies. And these are quite different in their characteristics. So for instance, this corresponds to the lifetimes of these qubits, and you see they span orders of magnitude. And then you have the logic success rate, which is also all around above about 99%. The one here that's got non-applicable is because topological qubits haven't been demonstrated yet. And so each of these qubits have their different characteristics, and so different scientific applications might make use of different types of qubits and different architectures to their benefit. So there's certainly a period, there's going to be a period or a long period of scientists collaborating with the people, the companies and the national labs that are actually fabricating and building and designing these quantum devices, because different scientific applications will have different needs, just as was the case when designing and fabricating classical computers. So the IBM series of blue genes emerged from a co-design effort between lattice QCD theorists and IBM, as an example. So if you look at what is currently available, so for instance, the D-Wave annealing machines, they're typically with about 2,000 superconducting qubits. Google is 72 qubit chip available. IBM has got a range of QPUs that can be used through the cloud. Intel is working on both superconducting qubits and making progress in silicon. IonQ, this is trapped ions, 53 qubit system with a promise of cloud access coming soon. Microsoft's working on Majorana topological qubits, and these are in development. And Rigetti has a number of, this number's out of date, these are now bigger numbers, with the potential of 128. So when it comes to field theory and quantum computing and quantum information, there's been, as again was expressed this morning, there's been rapid development and progress. This is just a very small number of the papers that have, and the works that have been performed in this area. It's really, this field is really taking off, and for good reason. And so the first paper, really thinking about simulating lattice gauge theory in a quantum computer, was Tim Burns and Yamamoto from 2005, and then there was a sequence of papers from John Preskill and Stephen Jordan and Keith Lee, and then recently this has now just grown exponentially in the number of papers. This is because the promise of actually getting these systems onto hardware and actually doing real quantum field theory calculations is really a real opportunity now. So the paper that caught my attention, and essentially took me out of classical computing into this new area, was a paper by Martinez et al. That performed a real-time dynamics of lattice gauge theory on a few-bit quantum computer. And so this was a fairly, on the scale of impactful for science, this was a small computation. This is a one-dimensional quantum electrodynamics with 4 sites. It was based on a trapped ion system, and it was to simulate a 2-spatial site Schwinger model. So this is interesting for reasons that I'll come to in a little bit. But the real thing that got my attention here was it was for the first time a real-time evolution on a quantum field. So what they performed was a computation of the number of electron pairs, starting the system with 0 in empty vacuum, and then counting the number of pairs as a function of time as you evolve the system forward in time, really on this quantum device. And so this was really a breakthrough calculation in my mind, because it was the first time you could really see dynamics of the quantum fields. So in nuclear physics, we had an equivalent time equals 0 event, if you like, last year. So this was the work by Oak Ridge team. They took the effective nuclear potentials that will allow you to generate light nuclei, including the deuteron. They took this, they then partitioned it up and put it onto a quantum device, and they could actually recover the binding energy of the deuteron within error bars. The result has no scientific impact in the sense that it's very imprecise compared to what you can do on a classical device, but nonetheless, this showed for the first time you could actually do a nuclear problem starting from known forces and then putting it onto a quantum device. And of course, the dream is that you can get to a quantum device to do a large enough system that you actually can't do on a classical computer. And since then, there's been a number of other, there's been developing computations. And so this one's interesting because if you look at the experimental program at Fermilab, for instance, and elsewhere, one needs to look at the response of nuclei to neutrinos coming in with GeV type energies. And that's a highly inelastic process. The nuclei tend to explode. And so this requires real-time evolution to perform this computation correctly. And so this is a first computation in a toy model showing, as you increase the number of qubits, your resolution of the spectral function. This is one of the things that's important in performing a computation is initializing the computer. If you just randomly set the computer into some initial configuration and ran it, you would just have you would be exciting all the states of the system. It'd be very difficult to get at the physics you're interested in. And so this idea was to couple basically to turn on a refrigerator. So you have a cold system here, and this is the system you're interested in, and then you slowly lower the energy of the system as a function of time, and because there's coupling between these states, energy moves from this system into this system, cooling this system and moving it closer and closer into the ground state. And so you repeat that cycle a number of times, and you can actually increase your probability of being in the ground state to of order 1. So something that I haven't mentioned yet is the concept of entanglement and the importance of this. This is obviously the subject of the meeting that's here. And this is something that really hasn't entered much into the area of nuclear physics at all until recently. And there's been a number of works that are interesting. This is work that came out of the European community. And so this was, if I take, for instance, 2 separated wave packets that are moving towards each other, and look at the entanglement entropy as a function of time, you see that as these packets collide, then eventually the entanglement distributes itself in this forward cone. And so this was one of the nice works that actually also got our attention. And then when it comes to fragmentation, of course, you're dealing with this highly energetic particle moving from some collision event, and so all the particles that are produced, of course, have some entanglement with all the others. And so there's work underway looking at exactly how entanglement evolves in these simple hadronic models at the moment, low-dimensional hadronic models of fragmentation. There's also more other work coming out of Europe that's directly impacted quantum computing for nuclear physics. This is nice work coming out of Bern and elsewhere. Solving QCD on a quantum device is hard. However, there's simpler theories that one can attempt to solve that have features that are important to nuclear physics, in particular bound states. So in addition to actually solving the theory directly to recover nuclei, there's a lot of technology that has to be developed on the way, and so working with simpler models that are accessible is an important stepping stone. And so it's been suggested that an SO3 interaction model for nuclear physics using ultra-cold gases would be a good way to start, and that looks really interesting. So if you think about QCD and what it's going to take and do the most naive thing, and so one should keep in mind here the slide I showed you before, where it took 24 billion years to do, and then after thinking about it for 3 years, it was reduced down to 1 week. So this is the 24 billion year equivalent of that, but for QCD. And if you want to do a lattice QCD calculation with all the quarks dynamical, with 4 quarks, U, D, S, and C, the 4 spin degrees of freedom and the 3 color degrees of freedom, and you just naively count the number of qubits to do a 32 cube lattice calculation, you're looking at about 4 million qubits. So this is a very big number. And so, as I said, to keep this in mind, this is like the 24 billion year estimate. So we expect this number to come down substantially as people think hard about how do you improve computations of lattice gauge theories. So this is sort of like the outer limit at this point. When this number came up, this just looked like mission impossible, but it turns out that in order to do some of the things that you need for encryption, you're looking at about 1 million qubits. So 4 million is not crazy. So state preparation is critical, because if you just randomly put down fields here, you would just have some highly excited state with tons and tons of excitations, and you wouldn't be able to pull out anything that you're interested in at low energies. So preparing the initial state, figuring out how to prepare the initial state in these non-abelian gauge theories is critical. Maybe conventional lattice QCD can play a significant role here. A lot of efforts put into preparing the vacuum state. But more likely, tensor methods and the other methods that are discussed at this meeting are going to play a crucial role in quantum computation of these field theories. So, and I'm running out of time, so I'll skip a few things. I've skipped that, actually. So low-dimensional gauge theories. So these are important not just for the physics, but there's importance. The studies of these non-abelian gauge theories are going to have importance for quantum information science also. If you want to design an error-correcting quantum computer, one should think about this as a quantum many-body problem, and most likely involving quantum field theory. And low-dimensional lattice field theories with gap topologically stabilized degenerate ground states are of interest in designing error-corrected qubits. So this lies at the intersection of condensed matter, high energy and nuclear physics, quantum information, and computer science. And so just as one example, for instance, the 2+1 dimensional U1 Higgs lattice field theory, the low energy sector of that theory is the same as Kitaev's toric code for error-corrected logical qubits. So again, as I said before, meetings like we had here, bringing these communities together, is going to be mutually beneficial, and certainly I look forward to more of these meetings. Let me skip this. So I want to say a couple of words about work we did with the Schwinger model in 1+1 QED on the IBM hardware. And so there's a nice presentation this morning. People in this room have done really impressive computations of the Schwinger model, and what I'm going to show you doesn't improve science at all. Okay. However, because it is such a well-known model and a simple model, it's worth putting this onto available quantum devices, just as Martinez et al. Did on the ions, to see how these devices perform on something that we actually know and have control over. So I undertook so I was part of a project led by Pavel Lugovsky, and this is my graduate student Natalie Clough. And so we looked at a two-site Schwinger model. This is the same computation as performed by Martinez et al. We used periodic boundary conditions, and the Hamiltonian for this system is very simple. It just has these terms. four terms. This is the energy of the electric field. This is the mass, the force into the antiferromagnetic ground state, and this is the kinetic energy term. And as far as QCD is concerned, it shares many of the features. It charge is screened, it's confining. The ground state has a fermion condensate, and it actually also contains bound states. So there's many, and the fundamental excitations are composite objects. So this is a good place to start worrying about how do you actually perform computations involving composite objects, and so on. So one can take this system. This is the Hamiltonian in terms of actions on a 2-qubit system. It's very simple, and then you can use Trotter evolution by applying multiple times your time evolution operator over a very small time interval. And the ideal curve, the perfect curve you know by exact solution, is the solid one. And the results that come off the IBM hardware correspond to these colored points. And the blue corresponds to extrapolated points that should be compared with the curve. And so let me comment firstly that when you create these quantum circuits, the gates are not perfect. And so as a result, one needs to be able to figure out how to remove these imperfections in the gates. And one of the ways to do that is to add more and more gates that are the identity and then extrapolate to 0. And so that's what these points correspond to. But the important feature of this curve is that after it gets to this time interval, the quantum device is decohered and is flatlined. So what you're seeing here is the device operating as you'd expect it to, and you can actually do error mitigation, and within uncertainties you recover the right answer, but then at some point you lose quantum coherence on the device, and then it becomes classical, and then you're done. So for the IBM hardware, we could actually take about 7 or 8 time steps applying these operations, and there's about 3 C-naughts per operation, so not many C-naught gates, and then the device fails. This is code. Okay, so you don't have to pay too much attention to this. This is code I wrote for Lattice QCD, just sophisticated C++ if you like. But there's a very low barrier for getting onto these quantum devices. It's just Python. It's very well laid out. So for instance, this is the circuit. This is the application of a C-naught gate, but of qubit 1 controlled by qubit 0. This is a rotation on the block sphere on qubit 0, et cetera, et cetera, et cetera. So actually the coding is very simple on these devices, so you can get on there easily and rotate qubits and then perform computations. I'm out of time. So let me summarize. So quantum computing, quantum information is now entering nuclear physics and HEP in the United States. There's really significant potential for disruption. With new understandings and capabilities, we can really start to now think about addressing these exponentially difficult challenges of finite density and real-time dynamics. And the lattice QCD techniques that we've developed since the 1970s can be applied for the Hamiltonian formulation for quantum devices, and that transfer's starting. And low-dimensional simple systems are now being stood up on both in simulators and on real devices. So it's important to recognize that the lattice QCD developments, the lattice quantum field theory developments, are going to impact quantum computing. Lattices of qubits required to define logical qubits and error correction are really quantum many-body systems, and quantum field theories are likely to play a critical role here. And then one takes into consideration the stability of topological field configurations. So thank you very much.
Martin, thank you very much for this fascinating talk that brought us from the beginning of the universe to most modern quantum computing. Are there questions, comments? Maybe I start. Do you think that this can also be helpful for high-energy physics experiments, like tracking traces of particle in the detector?
Oh, yeah, I would say so. So firstly, there's the quantum sensors and detectors part. On the hardware part, I suspect that will have significant impact. On the processing side, so at the moment one is starting to see, well, people are putting together machine learning and quantum devices, and I suspect that might be a way for the tracking to be significantly impacted also. But yeah, I do.
Very good, we take your word. Gavin.
Hi, thanks. Just on the quantum sensing part, I was just curious what they had in mind for that. Like those states that see the root end advantage also are very fragile to environmental noise. And so is there any sense of what context they would be used?
Yeah, so the environment is the big thing for all of these devices. And so in some optical, it's already been demonstrated in some optical lithography that in fact you can utilize an effect that's essentially this in sharpening the edges, if you like, and reducing the I'm not saying this well, but basically you can improve the resolution by a significant factor through quantum coherence in a phenomenon that's like this in optical lithography. So it's already been shown, and certainly in a number of other experimental settings, particularly cold atoms and various other setups like that, it's been well demonstrated.
And what would you measure in context here?
In this context, with the devices that I was showing. So it would just be, this would just be like any other detector. For instance, I measure I measure an excitation, and somehow I have to then measure, say, a de-excitation and read that out. So in this particular case that I showed, it's very similar in that regard.
In the curve you showed that flatlined after some point.
Yeah.
That was for the Schwinger model, right?
That was the Schwinger model, yes.
Is it possible to understand why the culprit is decoherence, but decoherence with what, and what are the processes involved?
Right. So if the natural decoherence, these machines have natural decoherence times in the first place. In this case, it's 50 to 100 microseconds, and the gate application time is roughly 100 nanoseconds or something like that. So each time you're applying a C0 gate, you're doing an interference between these two qubits, and it has a relatively large error to it, and eventually these errors will accumulate and then become random, and so.
But is it possible to imagine what would mitigate the onset of how it is possible to extend?
So that's beyond my capabilities. But if you look at the development of the superconducting qubits, then it's on a curve. It's on a curve that looks like Moore's law. So the devices today are exponentially better than what they were 5 years ago and 10 years ago. And
I think they call it Rose law, right?
Sorry?
I think they call it Rose law.
Rose law, yeah.
D-wave.
Yeah, there's another law. I thought it was Sholkov's law, but we won't get into that. But yeah, so that's on a curve similar to Moore's law. So that's expected to get better. I don't know what the expected limits are to that, though.
I don't see any question at the moment. I think we have coffee outside and we can discuss further with Martin. He's still here. And the workshop members, we meet again at 3:45. Okay, so let's thank Martin again.